involve a little geometry. Let's say, well, let me read you the assignment and then I write it. Okay, a farmer wants to use a length of 2,400 feet of fence to fence 3 sides of a rectangular area by the river. In other words, one side will be the river bank that need not be fenced, and the other 3 sides of a rectangular area need to be fenced. But you want to find the dimensions that maximize the area. In other words, you want to find the length and the width of the rectangular, 3-sided rectangular that maximize the area. So let's write the assignment. So here's the example. A farmer wants to use a length of 2,400 feet fence to fence 3 sides of a rectangular area by a river such that actually I prematurely wrote such that what I want to say is find dimensions such that the rectangular area, find dimension that maximize the area. Sorry about the writing, but okay, so find dimension that, remove that such, that maximize the area. So let's follow Polya's steps in solving this. And the first step was let's visualize the problem. Okay, so you have a river, and on this side we want to fence in a rectangle like so. Okay, so we'll call the length x and the width will be y, and the area inside, of course, is x times y. But we fence only 3 sides, so the river side, the river bank, remains unfenced. So what's given to us? What's given to us is really L, the length of the fence, is made of x, the length, plus 2y, twice the width, and it's equals to 2,400 feet. Okay? What we need to find is a dimension, find x and y that maximize the area. Okay, the area A. So A equals xy. Notice what we did. We determine a variable. So we determine x, y. L, of course, is the given quantity, and A is the area, xy, which is going to be our target function. We want to maximize A. Okay? So let's write here, we want max A. We write it like so. Okay, we want to max A. And in addition, well, since A has two variables, x and y, we need to reduce the target function A into the one variable, and we can use the length to reduce the variable, the two variables into one. For instance, we can replace x with 2y. So if L equals x plus 2y, I mean, we can replace x as a function of y, and L, we can solve for x and get x equals L minus 2y, or 2400 if you like numbers, minus 2y. So now the maximum, the area will be x times y, or 2400 minus 2y times y, or 2400y minus 2y squared. Okay? And we want to maximize this. What are the endpoints? Of course, one endpoint will be when y equals 0 or x equals 0. Okay? So if we look at endpoints, let's discuss endpoints. And you can see that in this case, the endpoints will be irrelevant. You may see it right away, because if y equals 0, then we don't have area. And so is when x equals 0, we don't have area. So because x can be the whole length, so x can be any number between 0 and 2400, and 2y, we can use the whole fence for 2y, so 2y can go from 0 to 2400, or y can be a number between 0 and 1200. But if y equals 1200, then x equals 0. If x equals 0, then we have no area, as well as when y equals area. So there is no area. So we're going to say the following, that the endpoints, since we have a single variable y, so we're going to say that A, when y equals 0, equals A when y equals 1200, and it's equals 0. So it's a minimum if you want to look for a minimum, but it doesn't contribute, the endpoints don't contribute to our solutions, so we need to find the critical number. And the critical number, of course, will be the derivative of A prime or dA dy, and here it will be 2400 minus 4y, and we set it equals 0, and y equals 24 divided by 4, y equals 600 feet. So if y equals 600 feet, then x equals 2400 minus 2y, and turn out that x equals 1200. So we're going to maximize A if x equals 1200 feet, y equals 600 feet. Okay. So that was almost an obvious problem. A similar problem will involve numbers. Very much like this one. For instance, it's almost identical, but has to do with numbers. Find numbers whose sum is 23 and whose product is maximum. So find two numbers. In other words, we can use 0, 23, that would be 0. 1 and 22, that would be 22. 2 and 11, 3 and 20, then the product is 60, and so on. So what two numbers give you a maximum, a product that is maximum? Well, here we don't need to draw anything, but if you think about it, it's very much like a rectangular, where one side, one number will be x and the other is y. So let's determine x and y as the two numbers. So let x and y be the numbers. And now what we have is the following. We have x plus y equals 23, and we want to maximize the product. We want to find maximum of x times y, but because x plus y equals 23, if we want to deal with only one number, then we can replace y with 23 minus x. And then the product, the target function, will be f of x, y will be simply x times y, and therefore f of x by itself will be x times y, or 23 minus x. So we have the target function will be 23x minus x squared. Once again, the endpoints mean nothing. If one number is 0 and then the other is 23, that will be a product that equals 0, so it's irrelevant. So endpoints x equals 0 and x equals 23 produce x times y equals 0. Okay? So all we need to be after is the critical number. F prime of x will be 23 minus 2x equals 0. Therefore, x is 23 divided by 2, or 11.5, and y equals 23 times, or 23 minus x, it's also 11.5. So the product is 11.5 times 11.5. Okay? So maximum xy will be 11.5 times 11.5.